Neil Gonadiwal, and this is my lab report on the magnetic field of a bar magnet. The purpose of this lab is to explore the correlation between magnetic fields and observable distance, both on and off the axis. We will do so by understanding the PHYS law, which relates magnetic fields with displacement and magnetic dipole moments to define the magnetic field of a dipole at any location, and we'll use this to model magnetic fields computationally. The central physical model used in this lab is the magnetic field, which is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. A function of the magnetic dipole moment, which points from the north to the south pole in the observation vector as expressed in the PHYS law, is used to express in the PHYS law. To determine the relationship between magnetic fields and distance, let's assume all values in expression are constants except r, allowing magnitude to be constant k to equal to constant k times r to the n, as shown on the right. A bar magnet is a magnetic dipole and will be treated as such in this lab. Here's a diagram of the setup. On the left, we essentially measured the distance for different dx's and plotted this data. On the right, we found the perpendicular distance needed for the magnitude of the magnetic field to be 100 microteslas, and then calculated the net magnetic field at the location shown in the diagram, which will later be compared to the results from the computational model. Now, to measure the off-axis magnetic field, we position the magnetometer a distance d-perp in the x and the y direction. We correct the y component by subtracting the magnitude of the Earth's magnetic field at that point. We get an average d-perp of 0.173 meters and a resulting magnetic field to be 1.76 times 10 to the negative 4 teslas. So here's a look at my experimental data, where I have my raw data as well as my graph of ln bx over ln r. To help estimate r, we needed to create a logarithmic plot of this data. The natural log operation creates the following transformation shown on the graph. The equation with r as an exponent becomes a linear function, resembling the y equals mx plus b pattern we're all familiar with. When performing a linear regression on the transformed data, we find the regression equation to be equal to y equals negative 2.95x minus 14.264. The coefficient negative 2.95 is n, which represents the slope of the graph, accounting for an approximately 2% error from the expected negative 3 value. The y-intercept is negative 14.3, which represents ln of k. We can solve for k itself by raising e to the y-intercept and then using that value to find the magnitude of the magnetic dipole moment, which comes out to be k divided by mu naught times 4 pi divided by 2. Using these numbers, I got a magnitude of 3.2 times Newton meters over Tesla. The glow script model. So moving on to the computational model, the first thing I did was to find a function for calculating the magnetic field due to a dipole with a given magnetic dipole moment in a specified observation. I used the formula I mentioned earlier, shown here again for reference, the PHYS law formula. I then set the location for 6 of the 7 points where I would be visualizing the magnetic field. Two of these are on axis, while the other 4 are perpendicular to the dipole axis. After that, I drew arrows for each of these 6 points as shown in the code here. Lastly, I did the same bit for observation location at a 45-degree angle off axis from the dipole axis. Here's the final result, showing 2 on-axis magnetic fields in orange, 4 perpendicular in light blue, and 1 45-degree off-axis magnetic field in purple. The arrows are scaled proportionally to the magnitude of the field they represent. The magnitude of the magnetic field at a 45-degree off-axis position is 2.83 times 10 to the negative 5. Let's compare that value to the value found in direct measurement. As we can see that it's not exactly the same, but considering the various errors and uncertainties in measurement, the fact that they're both to the power of negative 5 shows that we were successful in our calculations. We must also acknowledge there's room for further improvement that would allow us to achieve more precise data. Of the observations shown here, only the first and fourth experiments describe what I observed in my experiment. I noticed that when the magnetometer was far away from the experimented bx bx was close to 0, and when it was closer, bx increased as expected. So if I had an orange in my experiment to compensate for magnetic north, the magnetometer readings skewed to magnetic north would be skewed in the direction of magnetic north due to interference with Earth's magnetic field, which means the values of k, mu, and n would be less accurate. And if I were to stick 2 identical magnets together end to end and run the experiment again, The length of the magnet would be minimal, but the direction of the magnet dipole moment would be the same. Though we expect the magnitude of the magnetic field at surrounding points to be approximately doubled by some scalar constant, the results will be the same with only the magnetic dipole moment changing. Thank you.